Hello everyone, welcome to ECE 161. So once again, my name is Tolentino and we are going to discuss part 2 of lecture 9, Discrete Fourier Transform. So just a quick recap of what we've discussed. Basically, the DFT is representing the frequency domain of an um, aperiodic discrete time sequence in the frequency domain with discrete frequency values. So when we do that, we are actually making the original time domain sequence periodic with n. And we choose n. The number of points we should take from the continuous spectrum should be greater than the length of the signal L so that we do not lose time domain information and also to provide a good picture of the frequency spectrum. So we discussed some of the properties associated with the discrete Fourier transform. So first, an important property that you should remember is that if x of n and x of k are both DFT pairs, um, x of n and x of k are both periodic over n. Okay, so we've shown that a while ago or from the previous video that if we have x of n as this function, okay, we are now generating replicas of x of n with a period equal to n, the number of samples that we've taken from the frequency. And the frequency domain representation is also periodic with the same number. So n is always the period of both x and capital X. Okay. Number 2 is linearity. Okay, so this is fairly common for the also applicable to the other transforms like the Fourier, the Laplace, the Z. So it still applies for the DFT. So basically, when x1 and x2 are time domain signals and we take their DFT, the addition of x1, the DFT of the addition is equal to the addition of their individual DFTs. At the same time, if A is a constant and we multiply them by, we scale the signal, the time domain signal by A, we take the DFT of that, we are taking the same DFT and the same scaling, provided that A is a constant. Okay. Real. Okay. So this is like superposition. So this applies also to the discrete Fourier transform. So I will not prove this anymore, but basically, because of this equation, okay, n is 0 to n minus 1 x n e to the minus j 2 pi k n over n. And then you, this equation follows linearity, okay? So the proving is left for as an exercise. Anyway, number 3 is a new concept to us. So if you could recall, x1 of n convolution of x2 of n, if we take the, in this case, DTFT first. If we take the DTFT of this one, we get the product of their DTFTs. Okay. But if we are now getting the DFT, okay, this property does not hold true. We should apply actually a new operation. This is called the circular convolution operation. So capital X1 and capital X2, we multiply them, where capital X1 and capital X2 are DFT of X1 and X2 respectively. If we take the product of the two, then we take the inverse of that, we are getting actually the circular convolution of X1 and X2. So um, let us just try the operation of circular convolution so that we understand how this is done. So x1 is 2, 1, 2, 1, and x2 is 1, 2, 3, 4. We get the circular convolution of x1 and x2 of n. If we get the dft of x3, you have x3 of k. Um, this is equal to x1 of k multiplied by x2 of k based on the property a while ago. So we prove that by getting first the circular convolution of x1 and x2, and then take the DFT of that result, so we get capital X3. Okay, which should translate to the product of x1 and x2. So let's try it. So how do you do circular convolution? Okay, um, so the first step is actually to draw x1 and x2 on a circle. Okay, so for example, this one is x1, this one is x2. Okay, um, so in convolution, there are 4 steps, right? So we still follow those steps. So number 1 is we flip. Number 2 is we shift. 3 multiply. And number 4 is we add. Add because we are taking discrete signals only. Okay, flip, shift, multiply, and add. So in this case, how do we represent x1 in a circle? So in a circle, if you could recall, um, this is like Cartesian coordinate representation. So uh, this is our origin, okay, and then we move in the counterclockwise direction. So um, basically, if x1 is 2, 1, 2, 1, then we start here 2 and then move in the counterclockwise to 1, 2, 1. And then x2 is 1, 2, 3, 4. So the first step is to flip. So we choose a signal that we are going to flip. So for example, x2. So x1 is still the same. 2, 1, 2, 1. But x2 now is the flip version. So how do you represent flip in a circular sense? So um, this one. Okay, I'll explain later what this means. Okay, but basically, if you flip x2, um, you are now moving, instead of the counterclockwise direction, you move to the clockwise direction with the same origin. The origin is still at this point. So when we do that, if we flip x2, we have 1, 2, 3, 4. So that is the flipped version of x2. Now next is shifting. So the amount of shift basically dictates the index of x3. So for example, shift is equal to 0, then we are getting x3 of 0. Okay, so we get x1 still. We get x1 still the same, 2, 1, 2, 1. And then x1, x2 of minus n minus, let's say, n sub 0, where n sub 0 is the amount of shift. n sub 0 is in this case 0, so we just copy. Okay, 1, 4, 3, 2, and then multiply. That's the third step. We multiply um, we multiply this x1 and x2. So the multiplication is just element by element. So 2 times 1 is 2, and we follow the same indexing. So 4 times 1 is 1, 2 times 3 is 6, 2 times 1 is 2. Okay, and then last step is we add. So what we are going to add is the values of this in this circle. So the last step is add. So when we add them, 2 plus 4 is 6 plus 6, 12 plus 2 is equal to 14. X3 of 0 is now equal to 14. Okay. So that's it for the first index. So next is shift equal to 0. Shift equal to 1. So that is now we are getting x3 of 1. So we still have 2, 1, 2, 1 here, x1. But now x2 is negative n minus 1 modulo 4. So how do we do that? The shifting here is on the counterclockwise direction. So basically, you rotate this one. I'm not sure how to rotate it. But anyway, you get the picture. You rotate that, you get 1, 4, 3, 2. Multiply 4, 1, 8, 3, and then you add. You get x3 at 1 is equal to 5 plus 8, 16. And then you do it for the rest of the shift. So that's, we are left with shift is 2 and shift is 3. So we are getting x3 of 2. This is equal to 2, 1, 2, 1 multiplied by what is this? 2, 1, 4, 3. 2, 1, 4, 3. This is x2 negative n. Not sure if this is the right. Negative n plus 1 instead. Okay. Is that correct? Because the original is x2 minus n, right? Then we shift it by one sample. That is equivalent to x2 of minus n minus 1, right? So x2 should be n negative n plus 1. So this is negative n plus 2. Okay? This is equal to 6, 2, 2, 4. Add them up, you get x3 of 2 is equal to 14. And finally, let's add another page. Shift is 3 for completion, but I think you get the idea here. The idea is this one, x1 multiplied by, this now is x2 minus n plus 3. Minus n plus 3 modulo 4 3214 3214 equal to 8 3 4 1. Add them up, we have x3 of 3 is equal to 11 plus 4 16. So we have x3 of n is equal to 14, 16, 14, 16. If we want to represent it in a circle, we have this one. Okay, so that's how you do circular convolution. Okay, if you want to prove the property of this one, okay, let's try it. We have a result here. X3 is 14, 16, 14, 16. We verify using DFT properties. So first we get x1 of k. So let me just write the formula again. Xk is summation from n is 0 to n minus 1 xn e to the minus j 2 pi k n over capital N. So in this case, n is 4. Alright? We are getting 4-point DFTs. So n is 4. K is from 0 to n minus 1. So if we have x1 of n is 2, 1, 2, 1, then we are getting this function. The 2, 1, 2, 1 here is 2, 2, 1, 2, 1. And then take note, k is from 0, 1, 2, 3. So if you want to get this kind of expression, you should obtain x1 of 0. So for example, x1 of 0 is, substitute 0 in your k. Okay, so all of these exponentials is equal to 1. So 2 plus 1 plus 2 plus 1 is equal to 6. x2 of 0 for x1 of 2, x1 of 1, for example, substitute k is 1 in this case. We have 2 plus e to the minus j pi over 2 plus 2 e to the minus j pi plus e to the minus j 3 pi over 2. 2 is 2. E to the minus j pi over 2 is equal to negative j, I think. 2e to the minus j pi is equal to negative 2. And this one is equal to positive j. So in essence, this one cancels each other. And this is 2 minus 2. We have 0. How about x1? So for completion, let's just try the others. 2 plus e to the minus j, this is pi, plus e to the plus 2 e to the minus j 2 pi plus e to the minus j 3 pi. So 2 plus negative 1, this is negative 1, plus 2 times 1. So 2 minus 1, 1 plus 2, 3. What is e to the minus j3 pi? This is equal to negative 1. So we have x sub 1 of 2 is equal to 2. And you do x1 of 3, you should get 0. So x1 of k is 6020. Okay. Now how about x2 of k? x2 of k, recall x2 of n is 1, 2, 3, 4. N is 4, so we also have the same expression but different coefficients. So again, k is 0, 1, 2, 3. If we want to get x2 of 0, this exponentials goes to 1 because substituting k is 0 here. 1 plus 2 plus 3 plus 4 is equal to 10. How about x2 of 1? x2 of 1 is 1 plus 2e to the minus j pi over 2 plus 3e to the minus j pi plus 4e to the minus j 3 pi over 2. What is e to the minus j pi over 2? Once again, this is negative j. This one is positive j. This one is negative 1. So we have 1 plus 1 minus j2 minus 3 plus j4. We have negative 2 plus j2. So you do the rest for all of the k, you arrive at this expression. Finally, x3 of k, if we could recall, x3 of n, what we've done is, what we've solved a while ago is 14, 16, 14, 16. Okay. So we still have the same expression but different coefficients. So do what we've done a while ago, you get 60, 0 minus 4, 0. And you could see that this is actually equal to x1 of k is 6 multiplied by x2 of k is 10. 0 times this imaginary expression, 2 times negative 4. So we satisfied the property. So that is just the proof that circular convolution of two signals is, when you do the DFT of that, we are getting the product of the individual DFTs. Okay, so that's it for circular convolution. Now, a question that I want to provoke, or I want you to answer and reflect upon, is what if x1 um, has different length on with x2. So if x1 and x2 are of different lengths, how can we do circular convolution? Which is I want you to answer on your own, or I want you to reflect upon. And if you are not able to solve that answer, that's all right. Because I want you to post it in Piazza, and some students who have thought of an answer can answer it for you. So we will have a discussion, because I myself have an answer, but I'm not that sure of the answer, right? I'm sure there is an explanation. I have an explanation, but I also want to hear your opinions about this. So what if L1 is not equal to L2, where L1 is the length of x1 and L2 is the length of x2? So for example, diba 2, 1, 2, 1. What if 2, 1, 2, 1, 2, 1, and then we have 1, 2, 3, 4, and then you do circular convolution on both? So what will happen, or how can you do that? Okay, so I want you to answer that, reflect upon the question, and let us discuss it in the Piazza. Okay, so there you have it, circular convolution, some other properties. So time reversal, we've done this. Let me just explain a while ago what operation I did. So x of n, when you apply time reversal, you do x of minus n with some n. So this one is the modulo operator. So for example, n is 0, x of 0 time reverse, we have x of 0. Let's say n is 4. N is 4. Because we are familiar with the number 4, right? From the previous example. So, x of 0 is equal to 0. X of 0 is equal to the original, or the origin of the time reverse version is the original, right? So, what if n is equal to 1? Okay. What is x of negative 1 modulo 4? This is equal to x of 3, right? Because negative 1 modulo 4 is equal to 3. Is that right? So I hope you understand. How about n is 2? N is 2, x of negative 2 modulo 4 is the same. And finally, n is 3, x of negative 3 modulo 4. What is negative 3 modulo 4? That is equal to 1. Right? So, for example, a while ago, 1, 2, 3, 4, right? The time reversed of that is 1, 2, 3, 4. And we can see that um, x at n is equal to 1, this is n is equal to 1, right? That is equal to x of 3. And this one is equal to this one. This one is equal to this one. So, um, that's how you do time reversal. Instead of the counterclockwise direction, you go to the negative, to the clockwise direction instead. And that one, okay, is equal to actually this one. Okay? So, if we get the DFT of the time reversed, we are also getting the reversed version of the discrete. So, for example, let's have an example so that um, so for example 1, 2, 3, 4, this is x2, right? The DFT of that is x2 10 the ano the ano kanina 10 negative 2 plus j2 negative 2 plus j2 and then negative 2 and negative 2 minus j2. If we want to get the DFT of its time reverse version instead, okay, which is this one, 1, 2, 1, 2, 3, 4. Okay, the DFT of that is equivalent to the time reverse, the frequency reverse version of x2. So 10 minus 2 plus j2 minus 2 minus 2 minus j2. This is our x2. Let's say this is x2 prime. This is x2 prime of k. Okay, so that's how you do DFT reversal, time reversal in the DFT. Now we have other properties. So briefly, for example, circular time shift. Okay, let's say instead of this one, we get 1, 2, 3, 4. So what is that equivalent to? You rotate this by 2 units, right? 2 units. Just imagine with me, okay? Okay, when you rotate this one on 2 times, okay, you get this one, which is x2 of minus n minus 2 modulo 4. Okay, so the DFT of that is x2 prime of k, and then you multiply it by the amount of shift, e to the minus j 2 pi k times 2 divided by 4. Okay, so you can use this property if there is a circular time shift. And the rest, if you, it's just the same manner. So circular frequency shift, complex conjugate. Okay, so let's summarize. Okay, the properties actually of the discrete Fourier transform resembles the properties of our other transforms. So Laplace, Fourier, um, somehow they follow the same properties, right? Time reversal, circular time shift, multiplication, right, of this exponential, linearity. So the only distinguishing property is the circular convolution property. So that is fairly new to us. So I've discussed the process, and I hope that you understand the procedure. And also, to answer the question, I want you to answer the question, what if we have different length? Or if you could, if you can Google the answer. That's all right. And also to share it to your classmates, the answer. And that's it for lecture 9. So if you want further reading, you could read about these books. I've used the Provakis and Manolakis book for this discussion. So you could check out also the book by Mitra in the following chapters. So that's it. Thank you for listening for this lecture. This is once again lecture 9, Discrete Fourier Transform. And see you on the next lecture.